Hello, YouTube. We are back after a bit of a hiatus with, I guess, episode 80 of the Stanford MLSys seminar series. So it's been a little while since we've streamed, but we're very happy to be back this quarter. So this quarter, we're actually going to be this will be joint with CS 528 at Stanford. So if you're in that class, say hi in chat. We'd love to hear more from you, hear more about you. Later on in the second half of the quarter, we will also be going with Azalea Marhosseini's class on ML for systems. So we'll be sharing a lot of speakers with them. But to get us started today, we're very excited to welcome Mangpo from Google. So Mangpo is a staff research scientist at Google DeepMind, previously Google Brain. She leads the machine learning for ML compilers effort, which is one of the Google Brain moonshots from 2020. Previously, she received an undergraduate degree in computer science from MIT, PhD from Berkeley, Microsoft Research PhD Fellowship, Qualcomm Innovation Fellowship. So she's really at the center of this. We also have Simran today. So Simran will be co-hosting the podcast this quarter, and you may see her driving. So Simran, do you want to say hi?
Hi, everyone. I'm Simran. I'm also a PhD student in Chris Ray's group, and I'm co-teaching CS 229 with Azalea this quarter, so Systems for Machine Learning, and we're excited to have a host of speakers on the topic.
Yeah, so we've got a very exciting lineup for you this quarter. I think you can go to our website, mlsys.stanford.edu, to look at the full lineup and sign up for a mailing list. But with that, we're very excited to welcome our first speaker. So Mangpo, go ahead, share your screen, take it away. We're excited to learn about ML for ML compilers.
All right, thank you so much for the introduction, and thank you for inviting me to give a talk. I suppose that there's a break for a while, so I'm, glad that this is like the first talk, excited to be the first talk of the restart, and hopefully you enjoy and learn something new from this talk. And yeah, so I will be talking about my project on machine learning for machine learning compilers, which I've been working for a while. And let me try to see, hide this. Okay, that looks better. All right, so let's dive into this, right? So I guess that most of you probably know a little bit about machine learning system, but you may not, or you may know that one of the key components that it's really critical to making machine learning workloads run really fast is a compiler. And here is the overview of compilation stack for machine learning workloads at Google. And at the center, you can see XLA, which is a compiler that we use at Google to compile machine learning workloads. So it supports various front end, including TensorFlow, PyTorch, JAX, and it can generate code for various different backends, including CPUs, GPUs, and TPUs, which stand for Tensor Processing Units. And in this particular project, we are focusing on optimizing for TPUs because most of the machine learning workloads at compiler are running on TPUs. So that's going to be the focus of most of the work that I will be talking today. Now, the goal of this effort is to automatically select optimal compiler configuration for all the workloads running in Google Fleet for machine learning workloads. And why do we want to do this? If you look at a typical compiler, it's a tool that can transform program that usually written in high-level language that programmer write, and it will translate that to low-level representation, for example, binary or assembly that can run using the hardware. And throughout this process, the compiler will optimize the program during the lowering through a bunch of heuristics decision. Usually these heuristics are quite fast to run because when people click compile, we want the compiler to generate code, in a fairly short amount of time. So it's usually used like a linear or polynomial algorithm to decide the decisions for a very complex optimization, which means that these decisions made by the compiler can be suboptimal. And so instead of just rely on the compiler to make this decision, we believe that we can do better by searching through the space. So there we apply auto-tuning technique, which is a tool that can aid compiler to find better optimization decisions. So instead of relying on those heuristics, the auto-tuner will search in the space of all possible compiler configurations for a particular program it's being compiled. And it will try to find the best configuration according to a performance metric of interest. So we apply this technique to the XLA compiler for a good number of important optimizations, including layout assignment, operator fusion, a bunch of different flags in the compiler that control other compiler passes, and also low-level optimization, including picking tile size for each low-level kernel. Now, searching through these space of configurations can be extremely long, especially if the search space is large. And this is where machine learning comes in. We apply machine learning to help reduce the search time by using the machine learning or learn policy to help guiding the search towards the more promising space, and also use a learn cost model in place of evaluating the real program on the hardware. But first, let's take a look at some of these optimizations that we support auto-tuning and how we frame these problems as a search problem. So let's take a look at one of a popular optimization that is very critical and important in machine learning compiler. It's operator fusion. So let's take a look at a concrete toy example. So on the left-hand side, I show you a very small tensor computation graph that represents machine learning workloads. So each node is a high-level tensor operation. Operator fusion optimization can fuse some of these nodes together. So on the right-hand side, you can see that the add node gets fused to reshape and copy. So what does it mean to fuse these operators together? So for example, when we fuse add and reshape, it means that the intermediate output from add do not have to be saved in the main memory, but it can be consumed right away by the reshape operator, which means that we can help reduce the amount of memory usage required and also the traffic to the memory. But fusion is not always good because more fusion can also incur more computation. So in this example, you can see that when we fuse add to all of its consumer, reshape and copy, add have to be compute twice, right? So it incurred this extra computation. Therefore, this optimization is non-trivial because you have to balance between, okay, how much memory I can reduce without incurring too much extra computation, right? So the compiler essentially have to decide like what is the optimal fusion decisions. So the way we frame this as a search problem is first defining the configuration for fusion. So for each node, we annotate each node with a bit, either 1 or 0, where 1 means let's fuse that node with its consumers, and 0 means do not fuse. So in this example, we label add as 1, meaning that let's fuse add with its consumer, which is reshape and copy. Therefore, we control the compiler to fuse this graph in a particular way, so you get the resulting solution on the right-hand side where add is fused with reshape and copy. So I'm gonna just give you this one example and let's move to the result. So we support auto-tuning for different optimizations, including fusion optimization that I showed in the previous slide, but we also support tuning, layout configuration, how the tensor is laid out in the physical memory, and also other various flags in the compiler that control other optimization passes, and also tuning the tile size for each of the kernel. And in this experiment, we run the auto-tuner on the top workloads in our TPU fleet according to the TPU consumption time. And you can see here we report the average speed up on the top workloads. So we get about a few percent speed up on all of these optimization, which is quite moderate. However, these speeds ups are actually additive. So if we run all of the optimization tuning together, we're gonna get more than 10% for average speed up on all these top workloads, which is quite significant. And notice that it's average speed up, so some workload may not get much speed up, but some gonna get even much higher than 10% speed up. So that is quite promising. So we applied this technique recently to important production models that are recently deployed in this past year, and we are able to deliver 5 to 25% speed up on all of these models by just tuning the XLA flags. So that is quite an exciting result. But how can we really scale the benefit of auto-tuning to all workloads that run in our data center? Because usually we have to ask the user to run the auto-tuner for their particular workloads, which means that for an average user that run the workloads on our data center, they might not get the benefit. So to achieve this, we designed a system called AutoFDO for XLA, which is inspired by profile-guided optimization, where this is a system that essentially deploy the XLA auto-tuner at scale. So how does this work? In the first stage, we have Google-wide profile system that can tell us what is the top workloads that run on the fleet each day. Once we collect and have the list of the top workloads running in our fleet, then the system invoke the auto-tuner to tune these top workloads every day and save the best configuration as FDO profiles. We checked in these profiles into the compiler binary as embedded database, which means that when the compiler compiles a particular workload, it will first check the database if there is already a configuration for that workload. If there's a match, it will apply that configuration. If not, it will fall back to use the default heuristic configuration. Now, notice that we checked this in as part of the compiler binary. However, the compiler itself can change over time from version to version. So the tune configuration that is used to be best might not be best anymore, in a sense that if the compiler changed, maybe that configuration would actually give a slowdown instead of a speed up. So, and we don't want that. So we also build a profile called, which you can think of it as a garbage collector that will go through these profiles and configurations to make sure that the configuration is still better than the default configuration. And if not, it will remove that configuration from the database. So we have deployed tile size auto-tuning with AutoFDO for XLA to optimize the top workloads in TPU fleet every day. And we have been saving about 2% of total TPU consumption. And if you look at the saving ratio, it's about 15 times, meaning that we spend about 1 TPU to save about 15 TPU worth of time or compute time. And the key to enable us to tune at this scale is the learned cost model, which is where machine learning comes in, and it enables us to tune more than 20 times more kernels per day. So what exactly is the learned cost model? So let's dive into that, right? So the idea is that instead of having to evaluate the configuration candidate by compiling the program and run the program on the real hardware, can we predict its performance and use that instead? So this can significantly reduce the tuning time because it actually takes quite a while to actually compile and run the program on the real hardware. And here's the recap of the test of the learned cost model, right? So we have a particular machine learning program that we want to compile. This can be represented as tensor computation graph. And there are a bunch of different configuration where when you run which different configuration, you're gonna get a different time. And we essentially want to pick the configuration that have the smallest runtime. In some way, we don't actually care so much about the absolute runtime or like the absolute runtime prediction. We care more about the ranking of these config because we would like to identify that one config that gives the smallest runtime. Now, we experiment extensively with the idea of learned cost model on 2 of the optimizations in XLA compiler. The first one, I highlight them in blue. The first one is the layout assignment, and this is the optimization at the graph level. So you have the graph that represent the entire program, and you want to figure out the best layout configuration for that graph. The other one is loop tiling. In particular, we would like to pick the best tile size for our kernel. And a kernel is essentially a fuse operation together. I talked about operator fusion before. So when you decide to fuse operations together, it becomes one kernel, and a kernel essentially run independently from the other kernels. So essentially, the kernel level optimization, like loop tiling, are working at a much smaller graph. But anyhow, like the input to these optimization, they are both graph, which means that it is natural to use graph neural network to model this problem. So essentially, we can encode the structure of the program as edges in the graph, and also feed in additional information about each node. So for each node, we encode information, including opcode ID that represent what is the instruction of the node. For example, convolution, matrix multiplication, and so on, right? So that is the opcode ID, which we then encode using a learn embedding table lookup to convert the opcode ID into opcode embedding. And for each node, we also provide additional information as node features, such as the tensor shape for the input and output of the node, and padding, dilation information, and so on. So that also, that are all in the node features. The other information we give to the model is the configuration feature. So this configuration feature is essentially encoding the tile size and the layout configuration. So those are the input to GNN. The GNN would then produce node embeddings as output. Once we have node embeddings, we can summarize them or reduce them to the graph embedding. So it's just one vector of graph embedding, which we can then feed that into the feed forward layer and get the final runtime prediction. Now, we are interested in two types of evaluation metrics. The first one essentially is called top K error. Essentially, it represents what is the slowdown if we use the model to pick the top K prediction compared to the optimal configuration, right? And the second metric is the ranking correlation, which we use Kendalltown. And this will indicate the ability of the model to guide the search. Now, let's take a look at the results for the tile size runtime prediction, which is at the kernel level. And again, the kernel graphs are fairly small. Usually on average, they have about 10 nodes or a little more. So it's like a fairly small subgraph. So on this task, here is the top K error in terms of percent, lower is better. And let's take a look at just the first group, because there's a lot of information here. So in this chart, we report the top K error on both validation and test, and they kind of correlate quite nicely. In this experiment, we compare the different loss function that we use. The first one is MSE loss, or mean square error, and the second one is list MLE, that's in blue bar, and the MSE is in red. So you can see that using list MSE is much better than using MSE. And what is exactly is list MSE? Is essentially a loss function that care more about the ranking between the elements in the list. So it's one kind of ranking loss. We also experiment with other types of rank loss as well, and we see a quite similar performance. Anyhow, the lesson learned is that if you care more about, just the ranking of the configuration, but not so much about the absolute runtime, it is quite more effective to use rank loss instead of a typical regression loss like MSE. The next thing we try is different kinds of GNNs. And we do not see a lot of difference between different types of GNN. So here we compare GraphStage and GCN. But what matters a lot is how we provide the information of the configuration. So the first method is that we join the configuration feature with node features before we feed that into GNN. And we found this to be much more effective than joining the configuration later with the graph embedding after the GNN results. And this is actually quite intuitive, right? Because if we join early the GNN part of the model, we actually learn about those configuration. Whereas if we join this later, only the feed-forward layer would know about the configuration. The other thing we compare with is a very simple MLE model, do not have any GNN in there, and you can see that as we expect, using GNN is much more effective than using MLE. So we get quite a pretty good result for the tile size runtime prediction. So now let's see if we can also do this for other optimization, such as layout assignment. And this is much more difficult because it is at the graph level, and the graph can be, the entire graph that represent a program can be much, much larger than the kernel graphs, right? So which bring us to the questions on how can we actually train a GNN model when the input graphs are extremely large. So we are talking about graph that have 500,000 nodes, and we have seen this in practice. So how can we handle this? Now, if you train a typical GNN on a single accelerator device, you will surely run into out of memory problem because there are too many nodes. You have to keep the activations for all the nodes. So one simple solution that we try is to do graph partitioning and partition the graph into multiple segments. And then you feed each one segment into the learn cost model at a time to get the runtime prediction for that particular segment. And then you compute the summation of all of them to get the final prediction. Now, if you just do backward propagation, you still keep the activation for all of the nodes. So the trick is to only do a backward propagation on one of the segment and drop the WAC and do not save activation for the other segments. And interestingly, we found that the accuracy, compared to the full graph training, we don't see much accuracy loss. So this technique seems effective, and it can enable us to train arbitrarily large graphs without much accuracy loss. Now, the other issue that we ran into is that the graphs that we have to deal with are very diverse in terms of its structure. So how can we make our model generalize better to these diverse graphs? So we got an idea that, hey, we know that dropout is a very generic and general techniques that works pretty well at making a model generalized to unseen workloads. So we apply the same idea, but with a little twist, where instead of dropping out just some neuron, like values from some neurons, we are going to drop out an entire segment. So we select some of the segments and drop them, and then upweight the values from the other active segments. And it turns out that this actually works quite well. So you can see here on the bottom is the validation score. This one is the correlation score. So higher is better. And the green line shows the score of the segment training with the dropout techniques. And on the validation score, it is surpassing or doing better than just the segmentation methods. So then we use this technique to evaluate for the top K error metric that I explained earlier. So the best represent the model that do the segmentation and also the dropout. And you can see that it is doing better than the typical full graph training methods where you actually feed in the entire graph. And here, to prevent from out of memory issue for the full graph, we just drop the graph that it's too large. We also perform other ablation studies, such as the size of the segment, different ways to partition the graph, and those are the other rows in this table, which we don't have much time on, so I'm gonna just skip that. We have been experimenting with this data for a while and realized that it's actually very interesting. It also technically challenging, and it is quite unique compared to other data sets that are available publicly. So we recently released our data set called TPU Graphs Dataset to the public. And here is the scale of our data compared to other graph data out there, and you can see that it is quite large scale compared to the other ones. So if you're interested, this TPU graph data set essentially include the runtime data set on the two optimization that I talked about, the layout configuration and the tile size configuration. And it is publicly available on GitHub. And we are also currently hosting a competition on Kaggle on this data set. And the final deadline is November 17 with a pretty sweet cash prizes. And we hope to invite the winners to present at ML for System workshop co-located with NeurIPS this year, which I co-organized. And with that, I'm going to leave more information with this last slide, and I'm happy to take questions.
Great. Thank you so much for that presentation. You can go ahead and stop your screen share, and then we'll move on to the kind of the Q&A portion of it. And if you have some trouble turning the screen share, I think I have a way to turn it off, but
yeah.
Okay.
Ooh, yeah. Let's see if I can do this.
Okay, I clicked stop sharing on my
Okay,
end.
all right.
that should do it.
Thank you.
Great. So thank you so much for that presentation. It was really, really, really interesting. We're moving on to kind of the Q&A portion. So if you're watching on YouTube, you can leave chats in the YouTube. We've also got a few questions on the Discord channel for the students in the class. But I just kind of wanted to start off with sort of a high-level question that I was finding interesting as you were going through the talk. And that has to do with kind of how do you actually select those pieces in the search space? So you kind of talked about like fusion, tiling, things like that. How do you know when there's like, how do you decide like what are those things that you're going to search in the first place? And how do you like one thing I'm really curious about is, has your work ever found like, oh, there's this other thing that we need to optimize that people weren't thinking about before?
Yeah, very good question. So how do I select these optimizations to search for? I talked to the compiler experts, so people who build the compiler. There's a whole production team at Google, so obviously they know a lot more than I do. So I talked to them and I'm like, hey, do you think that there are opportunity on, making some of these optimization better? Like, do you think that there are headroom that the heuristic is not already optimal? And they don't always know. They don't know the answer. They only speculate, right? They would tell me that, oh, we think that there are some opportunity on fusion, right? I think that's the first one that they mentioned to me. And so I think it's like I collect these, information from talking to the experts. So then you have like a candidate list of things that you think it might be useful to tune. And then I start experimenting with the compiler. And before building the full-blown like auto tuner, right? What I do is that I kind of like introduce like a random number generator to alter the decision of the compiler, and just kind of run them like a bunch of times. And then if I see that, oh, there are some good speed up on some of the workloads, then that's an indication that, hey, there's some headroom there. So that's how I kind of like, pick which one to tune. And
Right.
there are some failure, like there are some optimization passes that we try to tune. So like with these, simple tricks of exploration kind of give us idea on like, oh, whether it's good to invest more time on this or not. Yeah.
Cool. One follow-up question to that, just because what I've worked on in the past. I wonder how would you think it would be possible to discover kind of maybe deeper algorithmic changes? For example, something like flash attention. Do you think there could be a compiler or an RL search or something one day that could discover, hey, this is a set of like facts that I know, like maybe you write down things like this is how you tile softmax or something, and then maybe we can discover that there are other operations that are IO bound or something that we when you first look at them, maybe it's hard to tile attention because you have the softmax thing, but I know this fact over here, so I can actually compute it differently, and maybe there's some speed up. Do you think we could ever be in a world like that where we could be automatically discovering like algorithmic changes as well as kind of these other things that are more standard to tune?
Yeah, I think it's possible. I mean, it's probably like not today or tomorrow, but I think if as people work in this space more and more, I believe that we can head towards that direction. And I think the key piece is essentially how can you make the system automate these things, right? Like you need a space for the system to work on. And obviously you can try to make the system write assembly from scratch, but like that's not gonna work, right? Like that you give a lot of flexibility to the system or like the model, right? So like it could do whatever, human can do, like write things manually. But that's not gonna actually work because the search space is just way too large, right? So I think the key question is that can one come up with a good abstraction that allow the system to only do these interesting transformation. And it should be like high level abstraction enough that the search space is not too large, but at the same time flexible enough that would do all these like algorithmic changes and also some of the compiler changes, right? And I think that require innovation or like what is the right abstraction. Yeah.
That's an exciting future.
Yeah, thanks for the great talk. One quick question before we jump into student questions is, you mentioned that the current savings with AutoTuner are around 2% of the TPU consumption, which is very exciting. And I was a bit curious on what is sort of the upper bound you would imagine with the current approach, and what are some of the main opportunities that you see for improving this number right now?
Yeah, so the 2% that you mentioned is the current saving that we have been delivered from just tile size auto tuning on the fleet graph. So it's only one of the optimization, and we are in the process of rolling out other optimizations tuning as well. But there are some system reliability issues, so we have not been consistently deliver what we hope for. But from our estimated average speed up, we have seen that if you actually combine all the things that we already support tuning, we expect to see like 10% or a little bit more on average. But that's mean that if all the workloads are actually applied to tune configuration, you're gonna see like a bit more than 10%, right? But in reality, it's really hard to achieve like all the speed up because the way that we hoping, the way that we deploy this at scale is that we save the configuration in the database, right? And then like when the new workload is being compiled, we shake the database. So, which means that, if there's a new workload that we have not tuned before, the configuration for that workload is not going to be in the database. So for those new workloads, they're not going to get the benefit right away. But eventually, if they become, if it's become like the top workloads in the fleet that we profile, then we're going to generate the configuration for those, and they will get like a hit of the configuration later. So essentially, there's always like a catch-up games where like we're not going to tune everything possible the first time it run, but eventually when it's run long enough, then it will become in the database. So there's a gap there, and we are experimenting with some new design on how to address that, to close this kind of like a hit rate gap. Yeah. So to recap the answer, if all the workloads actually use the tune configuration, we hope to see like up to 10% or even more, but that's really hard to realize. So something in between, 2 to 10. Yeah, that's the hope.
Should we move on to some of the student questions? I think they've got a lot of good questions today.
Yeah, let's do that. So one initial question from the students is, a bunch of us noticed that it makes a big difference if you join the graph and the config embedding sort of earlier or later in the process. And so one of the student questions is, what do the per node configurations include? And if you could shed some more light on that.
The per node configuration. So the node features, so there's a two portion of it, right? So like the first part, the node feature, just describe the arithmetic, computation of that node. Like for convolution, what is the window size, or like the kernel size for the convolution, like whether it's like 3 by 3, 5 by 5, what is the input and output channel. So there are such information, and also like what is the padding, what is the padding size, what is the shape of the input and the output tensor. So that all include in the kind of like the mathematic description of that node. And then the second part is the configuration parts. And this depends on the optimization, right? So for tile size, we essentially include the tile size for the input and the output. And for input and output, we include, I think, like 8 dimension of like six or 8 dimension of all the tensor. And this is because, you know, in theory, you can have a variable number of dimension for the tensor, but in practice, we rarely see things that it's more than 6 dimensions. So I think we only encode like the 6 dimension of the sizes, and we also include the product, so that that represent the volume of the tensor. So that's how we featureize tensor size. For a layout configuration, it essentially similarly, like we have the input and the output part of the tensor. So for each of the tensor, we also encode like 6 dimensions of how the tensor is laid out in the memory. So it's the order. So the layout essentially indicating which dimension is ordered in the physical memory, going from like minor to major dimension. Yeah. But yeah, I think it depends on the optimization, and there are actually different ways to encode this information, and by no means like what we do is probably the best thing. So I think that there might be other encoding that might give even better results.
Awesome, makes sense. So one of the students was interested in learning a little bit more about which types of Google products and workloads end up being at the top of the fleet, and how customers or users of Google might experience these compiler improvements. So more product side question.
Yeah, I'm not sure if I can tell too much, like share too much details about this. But I would say that the top workloads, as you may guess, what are the biggest things that use machine learnings in Google? You can probably guess. And there are a good portion of some of the resource going into inference model, the one that actually used to serve like user requests, and a pretty good chunk that goes into training those models. So those who are the top one. And there might be like some models that it's still not released yet, but it's still like under research, that might also consume a good amount of resource. But I would say in general now, most of the models are transformer based, because that's like one of the biggest innovation and there are already like many products that depends on it. Yeah. Sorry, I couldn't share too much more like details about this.
Based on what Google is known for, maybe search, maybe Gmail, maybe YouTube. I feel like these are all things that you do not have to confirm or deny, that are heavy workloads at Google.
Right. Yes.
Yeah, so one student is also curious about whether the auto-tuner or similar techniques are being applied for GPU workloads as well. I know that you're primarily focused on the top workloads in the fleet, and so I presume most of those are running on TPU. I'm not sure how many Google workloads are split, and whether there's a team handling that as well.
Yeah, we have not applied auto-tuning on our GPU workloads, but there is some ongoing conversation that like, oh, can we expand it to GPU? So we are starting to look into it. And definitely, I think there are also room for improvements on the GPU workload as well. And you probably see in, many papers from academia that also apply auto-tuning on GPU, and they are quite similar. One thing that is quite different from our work, from those work, is that they focus a lot on tuning at the kernel level, so at the subgraph level. So things that effective for both us and, paper that have published is that you would see like people always tune the tile size decision. So that applicable in any kind of actuator. For us, we kind of like scale it and tune decisions at the graph level, like fusion and layout, that I think a lot of paper have not focused a lot on. And it's because the search space it's much, much larger. And depending on the compiler that you work with, right? If you want to, able to control those decisions, the compiler will have to be able to support it. And like some of the compilers may not still, support arbitrary like fusion or like layout decision, because that's also depending on the ability of the low-level code generation. For example, I think in the past, a lot of compiler still depends on using like cuDNN and only like generate some form of like fusion kernel itself. So there is limitation on like, what kind of fusion you can support, and also what kind of layout you can support, because if you depend on kernel libraries, they're not going to support all types of layout configurations.
I actually have a follow-up to that. It's great that you brought up that last point. I wonder how much of this research is possible. Maybe you can speak to it because of kind of the let's call it the ML like framework stack that is used at Google. So for example, my mental model of PyTorch for a long time, at least maybe up until like Torch 2.0, is that because of like eager mode and all these things, it seems it would have been hard to build this type of system on a PyTorch stack. I wonder if you can speak to, the stack that you guys were developing on. Was it like TensorFlow or JAX, and like what is, or maybe it was lower level than all that, and what parts of those languages or frameworks made it possible or easier to do this research?
Yeah, definitely. I think the eager mode of PyTorch make things harder to optimize, right? Because you have to deal with a lot of dynamism. But as you say, with PyTorch 2.0, that they now have like a native compiler support, and what they do is that they like dynamically trace the workloads and actually turn that into a static graph. So it makes like each compilation unit static, right? So like once you capture the graph, then you can do all these sort of optimizations much more easily, right? So I think in Google, a lot of things are static. Like most of the workloads are written in TensorFlow and JAX. There is TensorFlow eager mode, but for at least for very important workloads, they tend to write a workload in a way that it's more static, so that you can define that, for this function, this is the unit of the graph, right? So it makes it easy to like capture the graph to optimize. And that's also true for JAX, right? So, and in some way, if you can think of like, if you have larger graph that you can capture statically, there might be more opportunity to optimize, right? Because you know more context about the entire graph. Where if you only capture graph at like a very small granularity, then you have a lot less option. Like to the extreme, like if the eager mode only like execute one op at a time, then you cannot perform fusion optimization, right? So that's like the extreme. But yeah. So yeah, essentially, like if you are able to capture graph at the larger granularity, there are more optimization to be done.
Great. I also had a question about, at some point you were talking about kind of the top K error and metrics like this. I was curious, kind of, you showed kind of various amounts of top K error. I wonder how that translates, like a certain amount of top K error will translate to like downstream speed up. Like if you're a little bit wrong, is that like, a little bit slower, or is there a cliff, or kind of, can you give us an intuition how to map top K error to kind of like speed up?
Yeah, right. Yeah, that's a very good question. And I did not have time to talk so much about these evaluation metrics. So I mentioned top K error and also correlation score, right? And I think that depending on what is downstream tasks or like the search techniques you try to do, I think one metrics might be more suitable than the other. So in like concretely, if your search space is small enough that you can just do exhaustive search and you can list all possible configuration, then I think top K error makes a lot of sense, because what it does, like the way that you use learned cost model in this case is that you enumerate all possible configuration, you use the learned cost model to predict everything, right? And you use the learned cost model to then select the top K. And for the top K, you then kind of actually validate it on the real hardware to pick the actual best one, right? And the top K score essentially tells you how far away from optimal if you use the cost model in this way to pick the top K candidate. So it reflects pretty much directly, like, okay, if you use the model to pick the top K, how far away from you being optimal, right? So that gives you a really good sense of, if you apply the learned cost model for that particular search space, you're gonna know exactly how far away you are from the optimal, right? So if you see 5% error, it means that, oh, you're gonna be 5% slower than the optimal, right? Now, if the search space is too large that you cannot enumerate everything, right? Then the top K error is not as meaningful, right? And that's where correlation score might be more suitable, right? So when you have this really large search space, the way that you're going to use the learned cost model is essentially you think of a typical search algorithm that you would use in this types of search space. For example, similar annealing genetic algorithm, where you try to like hill climb to the more promising part of the search space. And what you do is that, okay, you already have a candidate and you have a bunch of next candidate that you want to evaluate, and then you want to go towards the promising direction. So you want to be able to kind of like know whether the new candidate's better than you or not, right? So that's like ability to guide the search space towards the right direction. And that's why the correlation score seems a bit more suitable in that particular use case. Now, it is not clear to me exactly like what is the correlation score that would say that it's going to do well. In my experience, I would say that something higher than 0.6 or 0.7 means it's pretty good. Something lower than that, it's like you might not get a really good score. But this is only not very extensive. It's like some of the some number of experiments that I have run in the past. Yeah.
And one more follow-up to that, I think Simran has some great questions as well, is I remember way back in the Halide days when the Halide folks were going around and using it, or probably still using it, to write all the kind of computational imaging workloads on phones and stuff. One thing that they would look at a lot was how close could you get with like a Halide auto tuner compared to, let's say, like a very specialized like hand engineered pipeline. Say this is the most important workload at Google. Here's the best kernel hacker in the world, have at it. Like, how far are you from that kind of idealized solution versus what you can do now with auto tuning in your ML compiler?
Right. I would say that we don't really have that idealized solution in machine learning space, and perhaps it's because well, I think for Halide application, they target a lot of like image processing types of workloads, and there are some like really important kernels that they have to optimize for, and then the expert can spend a lot of time optimizing for that kernel, right? Now, I think in machine learning world, well, I suppose that at NVIDIA, you can think of CUDA kernel as those like very manually optimized kernel. Google take quite a different approach where we don't have like a specialized manual written kernel for TPU, but everything is generated by the compiler. So the compiler, it's kind of like, the baseline that we have. We don't really have like the manual super optimized version. I suppose that maybe there's some workload that people would actually like code the very low level there, but there are not that many of them. Yeah.
Somewhat related to the question is there one sort of learned cost model that's evolving over time and being applied to many different workloads? I know you talked about some techniques for generalization as well, but on the other hand, do you have sort of a suite of learned cost models or a method of like adapting or specializing to particular workload types?
Yeah, so we have one learned cost model that used in production for type size selection, and that one it's evolving over time, but not for different workloads. So it's kind of specialized to type size. There's some generalization in the sense that we share some part of the model for different TPU versions. So like the GNN part will be shared if it's for like TPU v3, v4, and so on, right? So there's some share part, and there are some like part that kind of like adapt for different generation of TPU, and then we have a way to kind of like evolve the model over time to adjust with the compiler change or the types of workload change that we see in the fleet. So we have this kind of like a fine-tuning pipeline setup that update our model like almost every day. So that's kind of evolving in some sense, but ideally though, like we probably want like a cost model that work for all types of optimizations in the compiler stack. And we do not have that yet, but I think we are hoping to head towards that direction. So the graph level learn cost model that I present, it's still not actually used in production yet, but we are hoping that if we can improve the accuracy of the model, it can be like integrated and used for the other optimization as well. Yeah.
Are there any other student questions that are to ask? Let's see.
Those were the
Big
main
ones.
Big ones.
Okay. In that case, let's see. There's a couple on YouTube. So there's one, I think, kind of hitting on one of the conversations that we had earlier. It's from someone on YouTube. They're wondering. Sorry, I'm looking up this way because that's where we have.
Sure.
They're wondering if there are automatic ways to determine kind of where the critical optimizations could be.
Well, one thing is perhaps taking information from profiling information, right? So as a if you want to optimize a workload as a human, what do? You like running the workloads, you look at the profiling information and you identify that, hey, that part doesn't look very efficient, right? And like based on that, depending on what exactly that looks inefficient, that will give the human idea on like, oh, perhaps these optimization could be better, right? Obviously, might not be like the average user, but if people who know the compilers somewhat well, they might be able to identify that and like pinpoint that, oh, maybe that optimization in compiler is not very optimal. And this is what we do internally when there's important workloads for important user. Like there are several experts that will look at the profiling information to try to help identify what we can do better. And sometimes it's the change of the model at the user programming level, but sometimes they have to like tweak the compiler, right? Now, perhaps if we have like an automated system that also can takes in these, profiling information, right, and understand the profiling information, and then it might be able to direct that, oh, it should spend more time tuning this particular optimization than others, right? Yeah.
Gotcha. There's a couple other questions. So one that I think is a bit more low level is kind of how do you determine which operations to actually fuse? Like kind of walk us through maybe like what that process looks like for the compiler. Like, is it like guess and check, or it's a mix of that and the cost model, or what does that process kind of look like?
So in the compiler heuristic, it essentially have like a very rough cost model. to decide like, okay, if these two nodes are fused together, what would be the benefit, right? So it have like a very rough cost model. So positive benefit, it's good, negative, it's not good, right? And then it kind of have like a priority queue based on this benefit. And then it will like pop value for the other to see fuse like C and A, then the benefit gonna be different before you fuse A and B together, right? So you have to keep updating this like queue. So it's like a priority queue based heuristics. And so you kind of like work with this priority queue until like nothing, there's no positive benefit anymore, right? So that's the heuristic that the compiler use, and you can see that it might not be optimal because the cost model can be inaccurate, right? And it might not understand like some other interaction that the cost model is not modeling.
Gotcha.
Yeah, whereas when we tune it, we kind of like force the compiler based on the configuration and just ignore these priority-based cost model.
Gotcha.
Yeah.
Cool. I think we're coming to the end of the hour, so just wanted to thank you again so much for coming. I'll end on kind of one higher level question, and then then we can say goodbye to YouTube. So just from a higher level, kind of what are you excited about in ML for ML compilers? What can we expect in the next years coming out of your group and coming out of kind of the field as a whole? What kind of excites you these days?
Yeah, I think there are definitely more application of machine learning in compiler, and we just only kind of like touch the surface and show what we can do, but there are a lot of dependency on analytical cost model in a compiler, or even the framework that is higher level than the compiler. For example, things that decide about like auto partitioning, auto model parallelism, and there are still, from what I see, a lot of inaccuracy when you use analytical cost model. It is also quite tedious, and it's like pretty painful to like maintain the analytical cost model to be like very accurate, given the new hardware, which is always coming out, right? So this is where I think the learned cost model could be really helpful, where like, can we do better than those analytical cost model, and also reduce the human time that's spent into like developing those analytical cost model. Maybe in the future, we will actually see the learned cost model being used as part of the critical path of the compiler, instead of just like using it for like tuning, right? And yeah, hopefully there will be more and more application of like machine learning in this space.
Cool.
Yeah.
And one last question is, if the viewers have more questions, they want to talk more, how can they reach you? What's the best way to hear about your work and ask more questions?
Yeah, well, I have a website, so it's my name, mangpo.net. My email is mangpo@google.com, and I don't have Twitter or X, so you will not be able to follow me there. But yeah, like if you have more questions, feel free to reach out over email.
Cool. Great. So thank you again so much for coming.
Thank you.
We're going to go ahead and wave goodbye to YouTube right now, and I'm going to click a little button that makes it go away. I'm just waiting and talking a little bit to wait for YouTube to catch up to the to the lag. But I think with that, we'll go ahead and wave goodbye and say goodbye to YouTube. Bye, YouTube.